think we'll get started. Um, so today is going to be more shiny stuff. We'll go through an additional technique for Bayesian computation and go through the process of implementing that in Shiny. And as we go through that process, we'll talk about some other bits and pieces that we haven't seen yet in terms of putting things together. And what those considerations are. So I don't have any slides to put together at this point. What I do have is I basically took the app that we put together last time and I made some small modifications to it just to clean things up and like to simplify things a little bit. And that is currently pushed to the exercises repo. So if you want to follow along, you can grab the current code from there. I've organized it where there is two different files for today. There's the _initial file, which is the starting point, and I'm not going to touch that. And then part one is what we're going to work on right now, and as we make changes to it, I'll save that and I will push that at the end. And then we're going to do a second version of it, which I'll call part two, that will develop off of part one. So there'll be those various sort of checkpoints along the way, so if you want to go back and follow along, you don't have to sort of reconstruct it from scratch as you're doing that. And so I'll mention that as we go, but the point is it's there. It's basically exactly the same app we were looking at before, just removing some of the pieces like the options and stuff just to make the code a little bit shorter. But otherwise, the basic logic there is in terms of doing the same stuff we were seeing before, updating it, tweaking things, so on and so forth. Okay. So where I want to start with is just to talk about another approach. So last time we were using this beta binomial model. It's sort of this canonical example of a conjugate prior where we define a particular prior given our likelihood function, and then in that happy circumstance, it works out that our posterior distribution will be the same distribution as our prior with just some new parameters that depend on both the data and our prior parameters. So that was nice, that all works well. What I'm going to talk about today is another method called approximate Bayesian computation, which is just another way of going about sampling from a posterior distribution given a particular situation. And so this type of approach is different. It's computationally intensive, it's inefficient, but it works in a much more general way where we're not constrained by the type of prior that we might put on things. So that's the ultimate goal here, is to be able to say, maybe I can't express my prior beliefs well with a beta distribution. I'd rather do it in some other way, and I would like to come up with a different prior and then figure out what the resulting posterior would look like by going through this process. Normally we'd use something like MCMC to do that. Here we're just going to offer another alternative approach, and in this particular circumstance it's fairly efficient to do and straightforward. So I will offer this to you as an approach without any kind of proof that it works. No theoretical derivations or anything like that. But what we will do is we'll show it on top of the ground truth of what we know works, and then just compare the results and see that they're compatible, and then we'll extend it to using a different prior distribution. So I'm just going to spell out explicitly what the steps are for ABC, and once we have that, we'll then go in and do the process of implementing those in the context of this particular example. So the first step is just going to be make sure that you define a prior and have the ability So I need to pick a prior distribution, I need to be able to sample from that prior distribution, and ideally I need to be able to do that efficiently because I'm going to need to do it a lot. So I'm going to need to generate many samples from that. Once I've got that, the next thing is going to be to define a data generative process. And so this is going to be something like the likelihood, but it's going to be more of a simulation type process. So what that means is it could be just a probability distribution, and that's what we're going to do in this case, but it doesn't have to be. What we need here for our data generative process is basically, think about it as a function where you give me a value of the prior, and then I can simulate the process that could have potentially generated the data that we saw. So for our case, we're trying to model coin flips here. So in that case, our data generative process is sampling from a binomial or flipping a coin with a particular fairness based on the probability that we got from the prior as the probability of success. But this extends, and you don't have to apply just in this circumstance. It could be anything here, as long as you have a way of generating the data from a value of the prior, simulating it in some way, randomly, then it's fair game for this particular process. And so that's one of the nice things of this particular approach is this doesn't have to be distributional. I don't have to write down what the probability distribution is or have a good model there. As long as I can simulate the data, I'm good. And that gives you a much wider variety of the types of approaches that you could use. In our case, it's still very simple. This is just drawing randomly from a binomial, but it's more general than that. Third step is generate a bunch of prior draws, which are then used to generate data draws. So I'm going to simulate a bunch of x's from this. And what we're going to then do is I'm going to take all of those prior draws that I had to start with. So again, for each prior draw, I'm generating one observation of the data. For each of those prior draws, I'm going to go through them and I'm going to filter them and keep only data draws simulate, take those, look at all of the data simulations that I generated. I'm going to keep only the ones that matched my data, either exactly or close enough, for an arbitrary definition of close enough. And if I then subset my prior draws for that, the distribution of that resulting subset will be the posterior distribution. So that's what I'm offering without sort of proof. But I'm going to claim that this is the case. That if we can go through this procedure and I do this filtering, whatever that remaining subset I have at the end is going to be equivalent to having drawn directly from that posterior distribution. That's the goal. So again, doesn't seem hopefully like completely out of left field that this doesn't make sense. Again, we're thinking about this whole process as, yeah, you have prior values that you observe, you draw those, they could have generated the data, and how likely they are to generate the data means how much I should keep them, and that's integrating both the likelihood or the data generative process and the prior together in a nice way. So hopefully it doesn't seem totally unreasonable that this is the case, but this is the kind of thing where it's very easy to get it wrong or to get something that's close but not quite right. So let's see if in practice this matches our observations from the true closed form mathematical derivation of the posterior in this particular circumstance. So for our Shiny app, what we're going to do now is add a couple things. So I'm going to add another heading where it'll let us specify the ABC parameters. And for this, basically, I'm going to have some more numeric inputs. The main one is just going to be the number of simulations. So this is the number of prior draws I'm going to make, and then the number of data draws I'm going to make from this, which I'm then going to filter down. So one of the issues here is it's very hard to specify ahead of time. If I want 1,000 draws from the posterior, I don't know how many simulations I'm going to have to run to begin with. I can just try a bunch of them. If I don't have enough, I keep going, that kind of thing. So this will be the number of simulations. And what we're going to start with is like 10,000. So this is a simple process, but it is a very inefficient process. Because again, the chance of exactly matching the data is quite low. And in this circumstance, we're in like the best possible thing because it's only in one dimension. As I get more dimensions, if I was trying to do this for something in 10 or 20 dimensions, the probability gets even smaller and smaller. Cursive dimensionality takes over. It gets harder and harder to do. But here, it's one dimension. It's only integers. We stand a decent chance of being able to do that, and so it should work pretty well. And that's where this approximate from approximate Bayesian computing comes in. It's deciding how close do you have to be to the data to decide to keep something or not. And the larger you make that envelope, the less accurate your posterior draws are going to be. That's the first one. We're going to add one more, which is going to be n min. And this is going to be minimum number of posterior draws. Basically, we want to have enough draws at the end so that we can reasonably approximate what that posterior distribution looks like. So in that case, we want to make sure that we're not getting too few. So let's make this 100,000 and this 1,000. So that's like a 1% efficiency. But even then, we're not going to necessarily always hit that point. OK. So that's these additional bits. In terms of our simulation, remember we had the first part that was generating this reactive object D. That was basically the derivation of that theoretical result and calculating the densities for the prior, the likelihood, and the posterior at each possible value of p. So from 0 to 1. We then take that and render it. So what I'm going to do here is basically the same thing, but now I'm going to create a reactive object for generating our ABC posterior draws that we can then add in. So this will be ABC posterior. It's again going to be a reactive. And this is going to then depend on those settings that are specified in that ABC section, so the number of simulations. So basically what we're going to do here is just implement those steps we described above. So ABC prior is going to be just a bunch of beta draws. So R beta, the number that we're going to use is going to be the number of simulations. And then we're going to use whatever the current values of alpha and beta are for our prior. So that's the first step. We have a prior. We can make draws from it. Second step is then the data generative process. So here, what we're doing is just simulating the coin flips. So in that case, ABC data gen is going to be our binome, and then filling in the various pieces here. So the number of draws we're going to do here is going to be the same thing. It's going to be the same as the number of simulations. And the size is going to be equal to the number of coin flips, n. And the probability is going to be equal to each of those prior draws we just made. So what this is going to do now is it's going to create 100,000 coin flips experiments to figure out what each of these things are. ABC posterior. So what we said is basically I'm just going to filter the prior values for the data generative process values that match the observed data. So that's going to be ABC prior. And then I'm going to filter this for ABC data gen. And so here we're doing exact approximate Bayesian computing because we're only keeping the ones where that exactly matches. We're not worrying about fractional differences or anything else. So that's just going to be equal to input $x. And at the end of this, what we're going to return back is just posterior. So what this is, previously before we were calculating the density. So for each value of p, we were calculating what the densities look like. This is now just a bunch of simulated values from that distribution. So it's observations of that posterior. And so what we want to do is we want to get a density from that. And the best way to estimate that is just using a kernel density estimation object. So what I'll do is ABC dense. And so what this is going to do is calculate a kernel density estimation of the points. So just to demonstrate that, if I do x is equal to r norm, and let's do 10,000 of these. Density of X calculates that kernel density, but if I plot it, it's showing me the approximate density from that. And so I can then recover the X coordinates and the Y coordinates from that, which I can then include in the plot to then have ggplot show it for me. So what I'm going to then return from this is going to be a tibble that's going to match the columns that we already have. So here, in terms of our plot, we're creating a data frame that has P for the x-axis, distribution, so previously that's prior, likelihood, and posterior, and then density, which is the y values that were observed there. So this is then going to just be P is equal to that density object, so it stores the x coordinates in $x. Whoops. The distribution is going to be ABC, posterior, and the density is going to be equal to ABC, Y. So the result of this is I now have this reactive object that depends on the various inputs that are explicitly there. And when I then call it and try to invoke it, it will return back the current value of that data frame as derived from that by running these simulations for me. If we then go down to our plot, what I'm basically going to just do is say that the data frame is going to be what I have here, and then I'm going to bind it to the data frame that I'm going to get from the ABC part. So bind rows is just going to glue the top part to the bottom part. Since the columns match, that's just going to work nicely. So this will be ABC posterior, but because it's reactive, I have to remember to call it as a function, not use it as a variable. OK, let's see if what we did there is going to actually work. Oops. So I forgot a comma, or oops. There we go. Try that again. And I typed an extra 9 somewhere. There we go. So something is going wrong in the R beta. But so again, this is an example where there's an error in my code. It's causing an error to be thrown in the R bit, but it's not causing the Shiny app to stop. It's still running, but something is failing as it goes. So let's take a look there. Invalid arguments. So this all looks reasonable to me. So again, one of the best ways to debug this, because again, I'm getting an error, but not a lot of context in terms of what's happening, is just to do print debugging. So something is wrong with these values. So I'm just going to print each of them and see if I can see what the problem is there. Let's just do this as separate print statements. So I'm not getting anything printed. Sorry, it was in the R beta, not the R binome. So, and so I was calling it alpha and beta when we were calling them A and B before. So the issue here is, and if we move these up, input and output are just list objects. They do more complicated things behind the scenes, but they are just being passed around as lists. So it's entirely possible to ask for an input that does not exist. And there's actually some power to that, and we'll see why in a second. But what then happens is if you ask for that, you're going to get a null value back if it's not there. So in this case, alpha and beta don't exist, so I'm getting a null, which I'm then passing into R beta, which is what's failing. But again, I was not getting that information at this point. It wasn't telling me what the values were, and that's why having to go in and do something like this helps. So let's fix that. So A, B. Now hopefully we're good. So unfortunately on the server, this is something that will happen from time to time. If you're running Shiny apps regularly, it will just kill your session. Again, if you're saving regularly, nothing should happen. Even if it kicks you out, you shouldn't lose any saved work. You just need to log back in and start it back up. I don't know what the cause is. It's hard to debug, but this is something that's been going on for a while. So hopefully it should work. And there we go. So the green line that's sort of hidden behind everything is the result of our ABC procedure. And it doesn't match exactly, but it's pretty close to the result. And we can try this with different things. So let's put this to 10. Not as good, but it's following along pretty closely. So one of the things that we might want to know is I'm asking for it to run 100,000 simulations, but I don't know how many draws from the posterior I got. So let's quickly just add a little bit of diagnostic output. So another kind of output to show what the result of this process is. So what I'm going to do here is below the plot, add a text output. And this is just going to call ABC summary, which will just print out this is how many simulations we ran and this is how many posterior draws we got. That will then look like this. And so what we're going to do is output $ABC summary. And this will then be, instead of render plot, a render table. It's going to be render text. So the idea here is, again, this function should just return text, which will then be rendered into the object on the page. Make sure I get this right. So what we want to do is we want to look at our ABC results and go through it. Is there a problem with that, though? So currently what this ABC posterior is doing is returning a tibble, but that tibble is the result of the kernel density estimation. So based on just looking at this tibble, I have no way of knowing how many values went into generating that density. So this is something that's super common to happen. You start with a fairly coarse level of reactive objects, but then you need an intermediate. But the nice thing is it's really easy to break these things up into smaller pieces. So what I can do is to say, okay, what I'm actually going to do now is ABC post is going to be the result of this bit. So I'm just returning those posterior values. And then I'm going to do ABC post density, which is going to be another reactive. And so this reactive will get the previous reactive, calculate the density of that, and then return a tibble. And then what I need to remember to do here is just make sure that I update that I'm now using density there. Okay, so now that we have this, I can take a look at this guy and basically say, okay, my output text is going to be as follows. So we ran input $nsim. Oops. This will just be actually the length of ABC post. So, cool thing again here is I can use any R code on any of these reactive objects as long as I'm in a reactive context. So I can bring this in, I can check its length to figure that out. So we'll do that, and say we want to summarize this, so we can say efficiency of 100 times length ABC post divided by input $nsim. So I can report all sorts of things. So this is going to calculate the percentage efficiency of like what percent back did I get from this. This returns a text. That should be fine with render text, so let's see if this is working. So I'm not currently seeing the text. Oh, yeah, that's correct. But I was not seeing an error there, so I'm not sure why. Let's just make the shorter render text. That all looks fine. There we go. I'm not sure why it wasn't doing it before. So what we can see here is that I ran 100,000 simulations and I only got 10,000 results. Not terrible, but that's only about a 10% efficiency. And what you can actually see is if you push this so that it's like where the data disagrees with the prior more and more. So in this example, so say I push this down to like 4, the efficiency is going to drop. Because again, as I make the data disagree with the prior more and more, the chance of generating a simulation that resulted in that sort of extreme outcome of the data is less and less likely. And so if I push this all the way to like 0, I'm getting only 122 results from this. And no, even that is enough to get something that's not terribly dissimilar from the posterior, but we're starting to see more noise because there's not enough samples to generate that density estimate accurately. And so this is why we included this minimum number, but right now we're not doing anything with that, right? Like that number is being completely ignored. So the question then becomes, how do we do checks or sanity things or give the user feedback in the app? So one example in like what we've done previously is to say, okay, if we go through here and if I get to the point where I am trying to calculate this ABC post density, and I can say, so stop if not length of ABC post greater than or equal to input $, what did I call it, and min. So this is the kind of logic that we would use previously, right? Run this. First bit of it is fine. Go to the situation we're going to not generate enough. And it does give us an error message in a somewhat appropriate place. So basically it knows that this is being called by the plotting function, and that failed, so it's going to like try to put the error message into the appropriate UI element where that was. But it's also not often the most sort of clear-cut kind of thing. The other issue is that it also shows up here. And so what we have is both the error and the warning sort of showing up. So the error happened, but Shiny's catching that and then issuing a warning to tell you that there's a problem. So this does work. It's not the most user-friendly thing, and you're a little bit constrained in terms of what you can do. So Shiny has a system built in for doing these kind of checks that's a little bit more robust and a little bit more designed to deal with sort of the vagaries of how all of this stuff works. And so instead of using this, what we're going to do is, so again, Shiny makes these functions available. There's this validate function. And so what the validate function then takes is a series of arguments of a need. So I need that the length of ABC post is greater than or equal to input $ and min. So this is the same thing that we had before. And then we can also include a slightly more user-friendly error message. So again, if you go back to like the tidyverse, like error message guide, tell the user what went wrong and then give them some guidance in terms of what they can do to fix it. So insufficient posterior draws. Oops. So sorry. There's need, and then the need is both the logical expression and then the error message that you want to associate with that not being met. And I've got an extra. So now when we run this, it's going to function in a very similar way. So let's cause it to happen. But now I don't get the angry red text, I get a gray error message. So it's slightly more user-friendly in that way. It does it in the same kind of thing where it puts the message in the right place. This is something that you could then also style with CSS to make it centered or bigger or do other kinds of things if you were so inclined. Note that right now this error message is just showing up here. If I changed where this test was, so let's take this and say, okay, instead of putting that validate here, I'm going to do, sorry, so I'm just going to keep it here but comment it out. Let's say that I put it at the end of this process, and now I will do that. What do you not like? Oh, sorry, I deleted one extra parenthesis. Okay. So now if we run it, what do we think is going to happen? Where is the error message going to show up? So this is taking advantage of the fact of that reactive graph. And because it's now higher up, the text output depends on depends on the ABC post versus the plot depends on the ABC density. So because I move this higher up, now both of these get invalidated, and I get the error message in both places telling you it can't do that calculation. For our purposes here, I would argue that this second option is the better one because it's nice to know if it failed, how many simulations, how many results did you get, what's the efficiency, because that's going to tell me something about how to increase it. So if I do this and it fails, say, okay, I only got 97, so I'm going to up this by an order of magnitude. So now that's sufficient. Go down, not enough. 10, not enough, so on. Okay, any questions about this? Okay, so the next thing that I'll show quickly is the idea of an action button. So this is not too bad right now, right? We're able to generate 100,000 or a million samples from the coin flips, basically like that. So the app doesn't lag very much, and that's okay. But if you think about it in terms of having to do this, if I'm here and I'm like incrementing this, like it's doing a bunch of computation every single time I move this, even though I probably don't care about the intermediary states, right? And this level of reactivity is fine, but sometimes we want a bit more control over all of this. So in that case, what we're going to do is basically to say, okay, I'm going to add another UI element here, and we'll call this run, and I'm going to add a new kind of input called an action button, and we'll call this run. So let's look at what that looks like. So basically this button, right now I click on it, nothing happens. So the idea of an action button is that it's basically a UI element that doesn't really have a value, but it triggers events. And so what you can do is you can cause other reactive elements to depend on that in some way, such that they will only update when you click that button. So we've already sort of seen something like this in terms of our earlier foray into this observe event idea. So here, basically, we're saying, I want you to update this thing, but I want you to only pay attention to this. So only when this gets triggered should you run things, as opposed to using something like reactive, which basically says you can include a bunch of other reactive items here. So those are inputs or other reactive values. And if any of them change, then this gets invalidated. We need to update the whole thing. But it figures it out sort of dynamically. And so what we can do is there's two approaches for this. So there are event reactives. So this is the same as idea as observe event, just the order of the phrasing is backwards. But that works in the same way, where you give it an event or an action, really another reactive that it then depends on. And it will only then update when that happens. Or alternatively, we can override when these things trigger by doing, and this is sort of the more modern, shiny approach for this bind event thing. So I take an existing reactive or observer, and then I can attach a reaction to it so it only depends on a particular thing. So in this case, I'm going to do this for D. I'm going to do bind event, input $run. And so really, action buttons, their entire existence is to be a reactive that other things depend on in some way that will then cause actions to happen. Bind event there, and we will similarly do it for so I don't need to add it to everything because I'm doing it to the upstream ones. So if I'm preventing them from updating, that will then mean that the ABC posterior density doesn't update, and similarly the plot doesn't update and the text doesn't update until I click the button. At least that's the idea. And I hope I'm doing this right, so let's see if that works. So note, nothing showing up, because they're all waiting for that event to happen. And so action buttons are slightly different than other things in that they do not initially trigger. All other inputs and other things, when they get instantiated, they created in the app, they will trigger their event once at least. So very often when you first launch your Shiny app, a bunch of stuff will run in a weird way, and you sort of hope you know what's going on. Often you don't. It's a little bit hard to know, particularly for more complicated things. But this is a really nice way of then preventing that to happen. So particularly if this was an expensive computation to run, And now I can click Run Simulation. It will go through the whole process. And note, now if I change any of these things, it's not updating when I do that. This is still happening because I didn't change that dependency, but the drawing of the plot doesn't change until I click Run Simulations, and now I got insufficient. Let's make it bigger, run it. There we go. So this is a really powerful idea in terms of sort of decoupling things and controlling when execution happens as it goes through. Any questions about that? So one other thing I will sort of demonstrate really quickly is about sort of input validation. So one of the things that you can often happen is this. So that got gotten rid of, and you're going to get something like this. So you cannot sort of fully idiot-proof an app. Somebody will always find a way of breaking it, of doing something you don't expect. But having a blank input or a bad input is not something that's wholly unreasonable to think could happen. And again, this is a little bit like worrying to a user of like, I broke it, something has gone terribly wrong. Even though if you came back in and did this, it will fix itself and it's fine. So that's still not enough. But so this is one of these things where we can do something to fix it a little bit, and it's actually quite easy. So this is another sort of very basic validation tool that we can add to Shiny apps. So basically, again, we're passing in values that are invalid, and we can check what they are. But generally speaking, again, with a numeric input, it's not entering a blank, it's giving us a null value. And we can verify that real quick. So this is happening at the R beta stage. So let me just print input nsim. So we can see what that value is right before that error gets triggered. So I'm getting an NA in this case. So something has gone wrong versus potentially a null. Maybe getting this slightly out of order. But what we can therefore do, or one of the things we can do about this, is we can provide tests at the beginning that validate that certain things are set in a nice way. Again, there are some things that you can somewhat constrain by the way in which you construct the input object. So sliders are good for that because they give you a defined minimum and a max, and the user cannot get it outside of that range, barring them like messing with the JavaScript or something. Numeric inputs are more general. They can take decimal values and all sorts of things, but the user can screw things up. So one of the simplest things that we can do is this rec, which is basically to say that we want a non-null value for this particular input at this time. So in that case, I can do require input $nsim. The thing I'm actually not 100% sure of at the moment is if that handles NAs or not. We'll try it and see what happens, and if it doesn't work, we'll come back to it in a second. So, so basically this is just saying that this reactive requires that all of these inputs exist at this particular point and are usable when we go. And let's try running that. So, didn't break anything, it still works. If I go back and try to do this, it's failing, but now without the error messages. So if I go back to R, there's no error message here either. So rec is basically the lighter weight version of that validate. And what it basically says is if I'm going through here, I'm going to write it very clearly. These are the inputs or the other reactive values that have to exist in order for me to be able to do the subsequent computations. And if any of those values do not exist, it just stops execution, and that reactive does not finish. So it just sort of drops out, but it does it in a way where you do not get an error message then. So if there was a problem here, and in this case with, say, nsim not existing, you'd probably want to use validate in the real world to give an actual useful error message. But for the quick and dirty, trying to avoid getting error messages, this kind of thing, rec is the really easy thing to add at the beginning to just explicitly say, these are the things that have to exist and be usable for me able to run the function, so I'm not going to get crazy behavior or something bad happening. So think about it if we were writing this out to a file or doing something else where it might have side effects. This becomes a much easy way to set up sort of guardrails to keep the input in a reasonable space for getting stuff out. The only downside of it is you just get a blank. So it makes it a lot harder to debug and know something has gone wrong or anything else. There's no reporting here as it goes. So you can take a look at the documentation for this in terms of what's there. So basically, in this case, it's sort of telling you how it's put together, what it looks like. But again, we can just string a bunch of these things, and they could be inputs or other reactive values as it goes through. OK. So what I'm going to do is I'm going to save this version of this file right now. And what we're going to do is we're going to split it and switch over to the next part. So what I'm going to do is just duplicate it. And we'll start working on part 2. OK, so part 2 is what we want to do here is basically come up with a way of doing what we've been doing so far, but now allow you to pick a different prior. So we're going to do this in a couple ways. So now with the prior, we have an issue of I have these options, but I need to do this dynamically because we're going to use either the binomial prior or we want to let people pick a truncated normal. So a normal distribution with a mean and a standard deviation, but that is truncated at 0 and 1, so that it still gives a proper probability as we go through that. And so what we need to do is allow the user to select that and then have different inputs for whether you're using the binomial or if you're using the truncated normal. So what we're going to do here is add a select input. So this is going to be the prior, and we're going to ask the user to select the prior. And the choices here, so a select input is going to be a drop-down menu with textual options that you can pick. The choices are basically going to be a named vector, where the name is what gets showed to the user, and the value is what gets returned by the input. So this will return lowercase beta, excuse me, but it'll show capital beta. And we'll show trunc norm equal to t norm. By default, the first option will be the one that's selected by default, but you could tell it to selected as one of these other values. So I could do selected equal to t norm. That would be the default option that's then selected. We don't need these at the moment. We will come back and use them somewhere else in a second. But the other thing that we're going to do is to say, OK, we want the UI to be dynamic. Previously, we showed a conditional panel, and we could definitely use that here. But what I'm going to show now is a dynamic UI where the UI is driven by logic that's within the server component of the app. So for that, we're going to use a UI output. And so this is just another kind of UI element. And it's just going to have a name that we can refer to in an output later on. So we're going to call this prior params. OK. So now basically what we need to do is include the logic that changes the UI based on which of those two options from the selection menu that they pick. I guess I can show you really quick what this looks like. Oops, UI output. So this is the selection input, just a drop down, and I can pick between the two. Call that full thing. OK, so in this case, what we now want to do is to set up something that will watch for changes in that input, and then based on that, change the output of the UI. There's a couple ways of doing this. I will show one, but again, this is not the only way. So let's just do an observer. So observe is just like reactive, but again, the idea of an observer is it's a reactive element. It just doesn't return anything. It just does something. It has a side effect. And what we're going to then do is say basically if input $prior equal to beta, we're going to do this. Else if input $prior equal to t-norm, do this. Else so again, strictly speaking, this shouldn't ever be able to happen. You're constrained by what's in the UI, but just to cover our bases, it's always good to be a little bit defensive and say, if it's something that I don't expect, throw an error. Okay, so what do we then do here? So basically, this is going to trigger when that input is changed. And what we are going to now do is basically do the output $, prior param equal to render UI. And basically, we're doing what we had done down below here with the reactives, where depending on the conditional, I'm now basically assigning to the output. And that's totally OK. That will then cause that UI element to update as it goes through. And so for this one, basically, what we're going to do is just put the two parameters that we previously had. With render UI, it just returns a block of UI elements. And we want to combine them together. So the easiest way to do that is just with the list. Because I want to return one object that contains all the UI elements I want. And so what this will now do is basically take that UI output and make it appear to be these two things. So it'll basically add a new set of UI elements for A and B like we had before. And then we'll do the same thing here. We will just render it differently, where now it's going to be a numeric input mu and sigma, prior mu, prior sigma. Minimum of 0, we'll set the default value for the mean to be 0.5 and the standard deviation to 0.25. Sounds reasonable. And yeah, that looks reasonable. And I mistyped observer. So note, when it launches, we see that beta, and now it's added those UI elements for me. I can change it to truncated normal, and it'll switch to mu and sigma. So hopefully this sort of gives you sort of a scratch in the back of your head that it tells you how powerful this is, because basically I can use my Shiny app to rewrite my UI dynamically. I can add whatever I want as I go through all of this stuff. So you can make incredibly dynamic apps in this way by just changing these things, and it's all just done through these UI elements. If you don't need to do it, it's better not to do this because it makes the code harder to understand. It's hard to figure out like what things are coming from where. But when you do need it, it becomes very nice as an option to do this, and you can do much more complicated things with it. We still have our thing, so that's running through and doing the rest. So the question then becomes, how do we wrap this up? Well, basically, I just now need to use those prior values in that logic to do what we've been doing. And so really, the only place I need to change that is in this sort of ABC posterior thing as we go through. So what I'm going to do here is basically return prior depending on what the setting of the prior is. So if input prior equal to beta, T norm, do that, and then else. So for simulating from the truncated normal, that's not something that's built into base R, but there are packages that do it. So trunc norm, R trunc norm, and then we can give it the various arguments. So this works in basically the same way. So input and sim, A and B here are going to be the lower and the upper bound for my truncation. So that's going to be 0 and 1. And then mean is equal to input mu. SD is equal to input $sigma. Oh, yes. I really want to type sum there for some reason. And we can run this. So run the simulations. That looks like that. We can switch to the truncated norm. So the only issue right now is we're doing the theoretical solution for the binomial with the beta prior. So when I change this, only the ABC bit is going to change, not everything else. So let's put it as like 0.1 and 0.1. Insufficient. So let's just crank it up. So there we go. Again, we don't know what this posterior should look like, but if we believe the procedure that we're using, all that I need to do is just change those initial draws, and this is what we get as a result. So something that's slightly different based on what that goes through. What we'll do now is just go through the process then of splitting this up a little bit so that we can get rid of any of the theoretical results and just look at the ABC component of it so we can compare things. So we can compare the two priors, see the rest of that. So what I'm going to now do is just like strip out a bunch of stuff. So we need all of the inputs. But what we do not need anymore is this bit, setting up that data frame. So I'm going to take that out. The other thing that I'm going to do is think about splitting up the steps of my ABC procedure. They are sequential, but they mean that I don't necessarily need to change the whole thing and rerun the whole thing if only a small thing changes, right? So if I change the value of x, I shouldn't necessarily have to rerun all of the prior simulations and all the generative simulations. I could just compare those existing values to what I have and then filter it out again to get the posterior. So what we're going to do is just break this up into each of those pieces. So ABC prior is going to be equal to reactive of this bit, and then just return ABC prior. So that gets us the first component. ABC generative sims, we'll call this, is now again going to be reactive. And that's just going to be binomial. That's fixed regardless of whatever procedure I'm using. But note now, I'm now thinning out in a large way the dependencies of each of these reactive elements. So instead of depending on all the things, it's depending on some subset. There's still clearly a hierarchy. It's going to have to go from prior to generative sims to posterior, but I don't necessarily have to rerun the earlier steps as we go. And then we will do the post as just that filtering step. But again, I need to remember to take the reactive versions of those things now. What I'm going to do is I'm also just going to get rid of this action button for the time being, just to make things quicker, simplify things a little bit. But That should be fine. Um, for this ABC density, what I'm going to do here is basically just simplify this by merging it all into the plotting function. We're just going to do each of the density calculations there as opposed to somewhere else. So I will just take that code, pull it out, and go with that. Okay, so for the plotting bit, we're still going to validate to make sure that we have enough posterior draws to go. But then what we're going to do is just construct the tibble for this. So we're going to get posterior density, the density function of ABC posterior. But what we can also do is get each of the other three. So this is going to be the prior density. That will just be ABC prior. So we're probably going to have a lot more of those than we need, but that's fine. And we'll have the likelihood density, which is going to be the ABC of the generative simulation results. Is that right? I think I'm... Sorry, for the likelihood, we do not want to do that. What we want to do is the calculation, we did it the other way. So again, we still know that that's a binomial with the various values of p, so we'll keep that one separate. So then the data frame is just going to be this collection of all of these things. So bind rows of, this is the posterior. The prior is basically going to be the same. I'm just using a different density estimation. So ABC dens of, so just the prior density, posterior density. And then for the likelihood, that's just going to be a tibble of zero to 1, 1,000 of those. Distribution is going to be ABC likelihood. And we'll just do the mutate of density is equal to E binom input x, input n, p. So that should be our full density, and then we've got the ggplot at the end. So there's a bunch of moving parts. It's a little bit much to keep it all in your head, but again, this is the kind of thing that you do it a lot more slow and steady and like iterate and try one thing at a time, print stuff out to see how it goes. But again, hopefully this is all good now, and let's see if it works. So I changed the names. Got to be careful about that. And I misspelled input. So at least in some of these cases, the error message is there. It's helpful for telling you what's going on. Okay, so the one thing we have here is we were back to that situation where the likelihood density, it's not a proper density because we're integrating over the wrong thing. So we could calibrate that, and I can go back and fix that in a second. But this looks similar to the results we were getting previously with just the purely theoretical result. But now, again, I can switch to the truncated normal and see what this looks like. So let's increase the number of simulations because that will always just help a little bit to get a slightly smoother thing. So I can center it there. I can center it at 0.1. So you can see the variations that you can come up with in terms of this. But the point is that we're getting something that looks reasonable in the end. So I can make the prior stronger by shrinking sigma in this particular case. And now, too small, but so we can shift them. Let me fix the density real quick for the likelihood. So for this, basically what we want to do is just take this value, and so we just want to normalize it so the area under the curve is equal to 1. So we can do that here by density divided by the sum of density divided by the number of entries that are there. So it's like the width of each of these bins. Whoops, wrong thing. Okay, so there's one last thing I want to show in this process that we need to sort of sort out. This dynamic UI works well. It creates things, removes them, it's all there. The one issue is, so when we run this, everything is fine. I'm going to switch over to trunk norm. And if you notice really quickly, the first time you open trunk norm, there's a little bit of an error message that flashes up on the screen. I'll try to show it one more time. So watch as I switch from beta to trunk norm. So as I do this, there's going to be a red error message for both the plot and for the output text. So if you look here, it's going to tell you what's going on. So basically, in the error trunk norm, r trunk norm, length mean greater than 0 is not true. So this is one of the things that can happen when we're using a dynamic UI like this. The issue here is that the input mu and the input sigma do not initially exist. They only exist after the first time we create those elements there. And so one of the issues that's happening here behind the scenes is, as my app has gotten more complicated, it's hard to know which reactive is going to trigger first. And so in this case, when this happens, the posterior ABC stuff is running first, and then that observer that's trying to draw the UI is running second. So what's happening is there's this brief moment where those UI elements do not exist. They're null, it fails, throws the error message. It then goes on to the next thing it can do, which is to draw the UI, which makes those things now exist. And by then updating them and creating them, it then causes that to trigger, which then runs the plot again, so then everything is fine. And these kind of circular things can happen all the time. They're really hard to avoid. It's really hard to know a priori in a deterministic way what's going to run first or not. And so this is an area where it becomes very important to basically include checks and using that rec function to sort of suppress those error messages. So if it starts to go through something and it can't find the element that it needs, it will just bail out and then let the other things run and then try again later on based on that dependency graph. So in this particular case, this is the thing where in the ABC prior, I would also strongly encourage you to include something like rec input mu input sigma, and we've already got the one for A and B, so that was sort of handling that situation. If we take those out, what you'll notice is this will then happen at the beginning when we launch the app for the binomial version of this. So it's not happening. Switch to trunk norm, it's fine. Switch back to beta, it's fine. But again, it's because there's this sort of lingering thing of, did it work, did it not work, that kind of stuff. And so this is where using things like rec becomes really important, because now this will clean it all up. So it's still doing the lingering thing of not showing beta initially. We can fix that, but I'll leave that as an exercise for you to try out, and we'll talk about it next time. I will leave it there. So all of the code for all of these different versions of it will get pushed to GitHub. I'll do that right now. So you can take a look at them, play around with it. The best way to understand this stuff is just to try changing things. You're not going to break anything. Comment stuff out, run it, see what happens, uncomment it, that kind of stuff. This weekend we'll be posting the next homework assignment. That will involve partly writing a Shiny app to do some stuff. Part of it will also be about interfacing with databases. We're going to do it all locally through something called SQLite. We will be talking about that in detail starting on Wednesday, but there'll be more than enough that you can get started on the first part of the assignment in Tuesday's class. So look for that posted by Sunday night or Monday morning. Start going through it. Reach out to your teammates. It'll be a new team and all the rest. But again, by the end of next week, we'll have covered all the material that's necessary to finish homework for. Okay, have a good weekend. I will see you all next week.
Yeah,